A frozen relic, billions of years old, is falling toward the Sun right now, and it is doing it faster, closer, and at a more extreme angle than almost anything we have ever recorded. On April 4th, 2026, Comet C/2026, A1, will plunge through the solar corona at several hundred kilometers per second, passing within 160,000 kilometers of the Sun's actual surface. The optimistic outcome is the most brilliant comet in over a century, a daylight object, a second sun, the kind of sky event your great-grandparents would have dropped to their knees for. But there is another outcome, a quieter one, and a small but serious group of scientists is watching for it very carefully right now, while mainstream media looks the other way. Stay until the end, because the reason they're nervous has almost nothing to do with the comet itself, but the Sun. If this story has you hooked, hit subscribe so you are here when Comet C/2026A finally arrives, because this story is only going to get bigger. Drop a comment telling me where you are watching from right now and what you think the Sun has in store for us come April. And if you want to help the Skylab grow, share this one. You are the reason we keep chasing stories no one else does. Now, let's get into it. April 4th, 2026, 1400 hours Coordinated Universal Time. Somewhere on the far side of the Sun, a frozen traveler from the edge of everything, a chunk of ice, dust and ancient carbon that has been falling toward this moment for thousands of years, finally arrives. It doesn't land, it plunges. At several hundred kilometers per second, Comet C/2026A1 tears through the outermost layer of the solar atmosphere, crossing within roughly 160,000 kilometers of the Sun's visible surface. To put that in perspective, the Sun's radius is approximately 696,000 kilometers. This comet isn't passing near the Sun. It is threading a needle in the Sun's own front yard, inside a margin that makes most astrophysicists instinctively lean forward in their chairs. Let's talk about what 1 astronomical unit actually means, because the numbers here need to land. 1 astronomical unit, 1 AU, is 150 million kilometers. That's the average distance from Earth to the Sun. The comet's closest approach? Between 0.005 and 0.01 astronomical units. Do the math and you get roughly 750,000 to 1.5 million kilometers at closest pass, and the photosphere, the actual glowing surface, sits right there waiting. The gap between this comet and the Sun's surface is, cosmically speaking, a rounding error. It was discovered on January 13th, 2026. By the MAPS survey operating out of Chile's Atacama desert. The discovery itself was already unusual. Kreutz sungrazers, and we'll get into exactly what that family is in a moment, are typically found when they are close to the Sun, often only days before perihelion, when solar observation satellites like SOHO catch them in their cameras almost by accident. C/2026A1 was detected beyond 1 astronomical unit from the Sun. Nobody had ever caught a Kreutz sungrazer that far out. That single fact told astronomers 2 things immediately. This object is unusually active for its distance, and it is probably unusually large. The early spectroscopic data confirmed the activity. Strong C2 emission, that's dicarbon, a carbon molecule that fluoresces brilliantly when energized by sunlight, was appearing at distances where most comets are still essentially dormant. Comets are, at their core, dirty snowballs. When they warm up, they sublimate. The ices turn directly to gas, dragging dust with them, creating that glowing coma and the iconic tail. But this kind of chemical exuberance at large heliocentric distances isn't normal. It suggests either a highly volatile composition, a physically large nucleus with more surface area to sublimate, or both. The estimated nucleus diameter, the solid core of the object before any of the glowing tail and coma, reaches up to approximately 2.4 kilometers. That may not sound like much, but for a Kreutz sungrazer in the modern observational era, that is enormous. These objects are fragments of a much larger progenitor that broke apart over centuries. Most of them are small. Most of them die quietly in the Sun. A 2-kilometer class nucleus in this family is the kind of number that makes people start doing new calculations. The brightness projections running through the planetary science community span a remarkable range. Conservative models suggest this comet could reach -4 in apparent magnitude, about as bright as Venus at maximum. That alone would make it a spectacular naked-eye object. Optimistic models, especially those accounting for forward scattering geometry as the comet passes between Earth and the Sun, push that number to -7 or beyond. -7. For reference, the full moon sits around -13. -7 would make this comet a daylight object, potentially visible as a bright streak near the Sun in the afternoon sky. The last time a comet performed at that level, the world was a profoundly different place. But here's the thing, and this is the part that the brightness predictions don't capture. The people watching C/2026A1 most intently right now are not the ones hoping for a beautiful sky show. They're watching because of something that has nothing to do with how bright it gets. They're watching because of when it's arriving, and what the Sun is doing right now, and what the combination of those two facts means for a civilization that has quietly made itself more dependent on solar stability than at any point in human history. The comet is spectacular. That's not in question. But the comet isn't the only story. The comet is the match. The question is whether anyone has been paying attention to the fuel. To understand why C/2026A1 is being treated differently, you need to understand the family it belongs to. The Kreutz sungrazers are not simply a collection of comets that happen to fly close to the Sun. They are pieces of a single ancestor. One enormous object, possibly many kilometers across, possibly more than one object, that broke apart over hundreds or potentially thousands of years, scattering its children along an orbital highway that leads, without exception, directly into the Sun. Heinrich Kreutz was a 19th century German astronomer who first recognized the pattern. Several dramatically bright comets shared nearly identical orbital characteristics: extreme inclination to the ecliptic plane, perihelion distances so small they graze the solar corona, and retrograde orbits, meaning they travel opposite to the direction of the planets. C/2026. A1 has a retrograde inclination of roughly 140 to 144 degrees, textbook Kreutz geometry, as if the orbital fingerprint of the ancient progenitor is still legible on every piece that fell off. The historical members of this family are not footnotes. They are legends. The Great Comet of 1882. Witnesses described it as a second sun. It was visible in broad daylight, a brilliant object hanging near the solar disk, bright enough that people who had never looked at a comet in their lives stopped in the street and stared. Astronomers monitoring it through filters reported that it passed so close to the Sun that the corona itself seemed to respond. Then there is Comet C, 1965, magnitude -10 to -11. -11. That is brighter than a full moon seen during daylight. Japanese astronomers Kaoru Ikeya and Tsutomu Seki discovered it independently, and when it rounded the Sun, it produced one of the most extraordinary visual spectacles any living observer had seen. Its tail stretched across a significant arc of the sky before dawn. And then there is Comet Lovejoy, 2011. This one deserves a moment. Going into its perihelion, models suggested it would not survive the corona passage. The combination of tidal forces, radiation pressure, and thermal stress at that distance were expected to disintegrate it. It went in anyway. It came out the other side. Not just intact, visually brilliant, its tail illuminated by the Sun in images captured by SOHO and the Solar Dynamics Observatory that remain some of the most remarkable comet photographs ever taken. Lovejoy was the object that made planetary scientists reconsider what they thought they knew about how these fragments behave inside the corona. The size question surrounding C/2026A1 is where the present story starts to diverge from those historical comparisons. There is an observational pattern, and it is worth framing carefully because it is a trend rather than a law that comets detected at greater heliocentric distances tend to be physically larger. The logic is simple. A small, dim nucleus doesn't trigger detection surveys at one astronomical unit. The fact that maps found this object that far out, combined with the early strong chemical emission, suggests a nucleus large enough to be losing significant material even at that distance. The estimated 2.4-kilometer diameter, if confirmed, would make this among the most substantial Kreutz fragments observed in the modern era. There is a data point worth noting here. Comet C/2024 S1 Atlas was, for a time, a candidate for a spectacular Kreutz Perihelion event. It brightened early and generated real attention. Then it began underperforming. Its light curve flattened, and ultimately it did not deliver the show that optimistic models had projected. That happens. Comets are famously unreliable. The icy, irregular, fractured nature of these nuclei means that outgassing behavior is non-linear. A comet can surge, stall, fragment, revive, or simply dissolve. C/2026. A1's light curve, by contrast, has been trending toward the upper envelope of predictions. Whether it holds that trajectory all the way to April 4th is genuinely unknown. If the nucleus is truly in the 2-kilometer range, and if it survives perihelion intact or fragments into several large pieces rather than evaporating entirely, the optical show could be historic. That is the part of this story that gets written about in astronomy magazines, but there is a second part of this story that doesn't get written about nearly as often. And to understand it, you need to think about what actually happens when a comet plunges into the solar corona at several hundred kilometers per second, not just to the comet, but to the environment it is entering. The solar corona is one of the most physically extreme environments in the solar system, and also one of the most poorly understood. It is the sun's outer atmosphere, extending millions of kilometers into space, and it does something that defies intuition. It is dramatically hotter than the surface beneath it. The photosphere, the visible surface of the sun, burns at roughly 5,500 degrees Celsius. The corona above it reaches 1 to 3 million degrees. The mechanism behind this temperature inversion is still an active area of research. The corona is where the rules change. In that environment, matter doesn't behave the way we experience matter. At those temperatures, atoms are fully ionized, electrons have been stripped away from their nuclei, and what you're left with is plasma, a fourth state of matter that responds not primarily to gravity, but to electromagnetic forces. The magnetic fields threading through the corona are extraordinarily powerful, reaching 1,000 to 5,000 Gauss in active regions, bending, looping, and containing enormous quantities of plasma in structures called flux ropes and magnetic loops that can extend hundreds of thousands of kilometers. This matters for C/2026 A1 because of what a comet actually does as it moves through this environment. The comet is outgassing furiously, releasing enormous quantities of water vapor, carbon monoxide, carbon dioxide, and other volatiles, all of which are immediately ionized by the intense solar radiation at that distance. This creates a plasma tail distinct from the dust tail, pointing directly away from the sun along the solar wind. But here's the part that connects to the central physics question. This ionized plasma tail doesn't just exist passively alongside the solar wind. It becomes electrically coupled to it. The comet, in a sense, becomes a conducting filament inserted into an environment already threaded with powerful magnetic field lines. The question, and it is explicitly a question rather than a finding, is whether a large cometary plasma injection into a magnetically stressed region of the corona could act as a perturbation, not as a direct cause, but as a trigger for an instability that was already approaching a threshold. In 2011, when Comet Lovejoy made its corona passage, SOHO recorded a coronal mass ejection in temporal correlation with the Sungrazer's perihelion. A CME is exactly what it sounds like. The sun ejects a massive blob of magnetized plasma into space, a billion-ton cloud traveling at potentially thousands of kilometers per second. The 2011 event generated real discussion. The mainstream consensus landed firmly on coincidence. The sun produces CMEs regularly, and during solar maximum activity, the timing of any random event correlating with a CME is statistically unsurprising. There is no peer-reviewed paper that establishes a causal mechanism by which a comet triggers a CME. That needs to be stated clearly. But there is a minority position within the heliophysics community, not a fringe position held by people in tinfoil hats, but a legitimate open question held by credentialed researchers that asks whether cometary plasma injection could, under specific conditions, provide the perturbation needed to initiate a magnetic reconnection event in an already unstable flux rope. Magnetic reconnection is the process by which magnetic field lines of opposite polarity snap and reconnect, releasing enormous energy. It is the primary mechanism behind both solar flares and CMEs. The field lines don't care what pushes them past the threshold. A sufficiently large plasma filament in the right location at the right time is at least theoretically capable of being that push. The fragmentation wildcard makes this more complicated. If C/2026 A1 doesn't arrive as a single object but as several large pieces, which is not unlikely given the tidal and thermal stresses at these distances, then the corona doesn't receive one plasma injection. It receives multiple simultaneous plasma filaments threading through the magnetic structure at different angles. The plasma interaction becomes more complex, more distributed, and by some arguments more potentially destabilizing to an already stressed field configuration. There is a geometry note that genuinely reduces concern here. The perihelion on April 4th will occur on the far side of the Sun, relative to Earth. This means that even if a CME were triggered at that moment, the geometry of the event significantly reduces the probability that it would be directed at Earth. Far-side events still affect the solar wind and can rotate into Earth-facing geometry as the Sun rotates over subsequent days, but the immediate threat window is substantially lower than if perihelion were occurring on the Earth-facing hemisphere. So the probability chain is this. The comet perturbs the corona was already at instability threshold, reconnection occurs, a CME launches, and it is aimed at Earth. Each link in that chain is individually plausible but uncertain. The combined probability of all of them occurring together is low, but low probability is not zero probability. And the reason that low probability is worth discussing at all has nothing to do with the comet. It has everything to do with what's already happening on the Sun and what it would mean if it happened right now. The Sun runs on an approximately 11-year cycle of magnetic activity. At solar minimum, the disk is quiet. Few sunspots, few flares, relatively stable solar wind. At solar maximum, the magnetic field has wound itself into increasing complexity. Sunspot groups cluster across active latitudes, and the rate of flares and coronal mass ejections climbs substantially. Understanding where we are in that cycle is directly relevant to understanding why April 4th is being watched so carefully. Solar Cycle 25 was, based on official forecasts from NOAA and the International Solar Energy Service, supposed to be modest. Analysts in 2019 predicted it would be similar to Cycle 24, which itself was one of the weakest cycles in a century. The forecast called for a moderate peak, an unremarkable maximum, and a solar environment that would give satellite operators, grid managers, and space weather forecasters a relatively manageable period. That forecast was wrong. Not slightly wrong, substantially wrong. By 2024 and 2025, Cycle 25 had exceeded projections in almost every measurable category. X-class flare frequency, X-class being the most energetic category, spiked well above predicted rates. The active region count stayed elevated longer than models suggested, and in May of 2024, the Sun delivered a G5 geomagnetic storm, the most severe category on the scale, the first G5 in roughly 20 years. Auroras were visible as far south as Mexico, Texas, and Florida in North America, and across similar latitudes in Europe. People who had never seen the aurora in their lives were photographing it from their backyards. It was beautiful. It was also a demonstration of exactly how much energy the Sun can dump into Earth's magnetic environment when it decides to. The solar maximum window that was supposed to be brief extended into 2026. Sunspot groups that had quieted temporarily reappeared. Machine learning models applied to flare prediction, a genuinely advancing field, improved lead times for individual flare events, but the fundamental problem remains. We can predict that the Sun is in an elevated state, we can watch active regions develop, but we cannot reliably forecast the timing and magnitude of specific CME launches, more than perhaps a day or two in advance, and often far less. The Sun, at this scale, is still largely telling us what happened rather than what is about to happen. This is the multiplier. C/2026. A1 is not arriving during a routine period of solar activity. It is arriving during a solar maximum that already surprised us once with how aggressive it was willing to be. The corona it will plunge into on April 4th is not the same corona that Lovejoy entered in 2011 during a quieter phase. It is a corona that has been producing X-class flares at elevated rates, that is threading active flux ropes through its structure at higher than predicted frequency, that has already demonstrated in May 2024 that it is capable of G5-class energy releases. No official body, not NASA, not NOAA, not ESA, is forecasting a catastrophic event around April 4th. That needs to be clear. This is not an official warning. This is a confluence of circumstances that scientists who track solar physics are noting in the way that careful people note when several independent systems are simultaneously under stress. The comet is one variable. The solar maximum is another. Neither alone is the story. Together, they define the window, and that window is opening into a world that is substantially more exposed to what comes out of it than any previous generation ever was. On September 1st, 1859, a British amateur astronomer named Richard Carrington was sketching a group of sunspots through his telescope when he observed a sudden, brilliant white flash erupt from the solar surface. He was one of only 2 people who witnessed what we now call the Carrington event, the largest geomagnetic storm in recorded history. Within hours, the CME reached Earth. The consequences were immediate and dramatic. Telegraph systems across North America and Europe began sparking. Operators reported receiving shocks. In some locations, telegraph paper caught fire. In others, operators discovered they could disconnect their power supplies entirely and continue transmitting because the induced current from the geomagnetic storm was sufficient to operate the equipment on its own. That was 1859. The telegraph was the critical infrastructure of its time. It was also, by modern standards, laughably simple. Single wires, simple switches. No microelectronics, no semiconductor architecture. The system was disrupted, but it was not destroyed in a way that couldn't be recovered from relatively quickly. Now, imagine the Carrington event hitting on April 5th, 2026. Not the comet causing it, just a natural Carrington-scale event from an overperforming solar maximum. The world it would be entering is unrecognizable compared to 1859. The modern electrical grid in the developed world depends on high-voltage transformers, enormous custom-built pieces of equipment that step voltage up and down across transmission networks. These transformers are not mass-produced widgets. Many of them weigh hundreds of tons, are custom-built for specific installations, and have lead times of 12 to 18 months, sometimes longer, to replace. A significant geomagnetic storm induces what are called geomagnetically induced currents, ground-level electrical currents that flow through long conductors like power transmission lines, pipelines, and railway tracks. For high-voltage transformers, these currents can saturate the core, overheat the windings, and in severe cases cause permanent physical damage. A sufficiently powerful event could simultaneously damage transformers across wide geographic regions. The replacements don't exist in a warehouse somewhere. They would have to be ordered, manufactured, and installed. The interim period, weeks, months, potentially longer in extreme scenarios, would be a grid outage at a scale modern society has never experienced. Lloyd's of London published a report in 2013, and the infrastructure baseline has shifted considerably since then, estimating that a Carrington-class event could cause between $0.6 and $2.6 trillion in economic damages in North America alone. That number is almost certainly outdated in the direction of underestimating the problem, given how much more embedded digital infrastructure has become in the decade plus since. Satellites are a separate layer of exposure. Since the Lloyd's report, the number of operational satellites in low Earth orbit has grown enormously. Starlink alone has deployed thousands of satellites, with more launching regularly. In February 2022, a relatively modest geomagnetic storm, not a G5, not a Carrington, caused SpaceX to lose approximately 40 newly deployed Starlink satellites because the increased atmospheric drag from the geomagnetic disturbance caused them to re-enter before they could raise their orbits. A modest storm, 40 satellites. A Carrington-class event aimed at a modern constellation would be measured in a different order of magnitude. Then there is the timing dependency. GPS signals are not used only by navigation apps on phones. The microsecond-level timing signals from GPS satellites are the backbone of synchronization across financial trading systems, cellular networks, power grid management, and internet routing. A sustained disruption to GPS accuracy or availability, and geomagnetic storms do both, cascades through systems that most people have no idea are GPS dependent. Financial transactions that require precise timestamps, cell tower handoffs, grid phase synchronization. The interconnections are invisible until they break. None of this is a prediction about April 4th. No one is saying the comet will cause this. The point, and it is the actual point of everything in this section, is that the vulnerability exists completely independently of the comet. And the comet only matters at all in this context because of what it is arriving into. A large sungrazer entering the solar corona during a modest, quiet solar minimum would be a spectacular astronomical event, and nothing more. The same object arriving during an overperforming solar maximum, in a corona already producing elevated CME rates, in a world that has quietly built its critical systems on foundations that were never designed to survive a Carrington-class event, is a different conversation. The comet is a flashlight pointed at a gap that was already there. If all of this sounds like the kind of thing that would be generating significant mainstream media coverage, you may be wondering why you haven't heard much about it. The silence is real, and it is explainable, and it connects directly back to what makes this specific situation unusual. In 2013, Comet Ison approached the Sun surrounded by extraordinary hype. It was predicted by some to become the comet of the century. Amateur astronomers cleared their calendars. News organizations ran enthusiastic stories about the potential sky show. Ison entered Perihelion on November 28, 2013, and did not survive. The fragments that emerged from its solar passage were too small and too faint to deliver anything close to what had been promised. The comet of the century became a case study in how badly astronomical predictions can misfire, and the media embarrassment was real. The institutional memory of Ison is still operating. The editorial threshold for a speculative story about a comet-corona interaction mechanism, which has no peer-reviewed confirmation, is high enough that most science journalists are simply not going to publish it. That is not suppression. That is editorial judgment, and for the record, it is not obviously wrong. The plasma perturbation hypothesis is genuinely speculative, and presenting it as a forecast would be irresponsible. What is interesting is the geographic distribution of the coverage that does exist. Japanese science media and certain European space weather communities have been tracking C/2026 A1 with more active public discussion than English language outlets. This may reflect cultural differences in how speculative risk is communicated, or simply different editorial traditions around space science. The public data is completely accessible. JPL's Orbit Viewer will show you exactly where this comet is at any moment. SOHO's real-time coronagraph data will be publicly visible as perihelion approaches. Anyone who wants to watch April 4th happen in near real time can do so. The silence in mainstream media is not hiding anything. It is the cognitive bias that affects all of us when confronted with low-probability events. We are not built to assign serious emotional weight to things that probably won't happen. The fact that they might is abstract. The fact that we have a comet that might look like a second sun is vivid. One of those things gets written about. The other one requires sitting with uncertainty, and uncertainty is hard to package. On the outer edge of the conversation surrounding Solar Cycle 25's overperformance, there exists a category of hypothesis that is worth briefly acknowledging, not because it belongs in the same framework as the verified physics we have been discussing, but because it keeps appearing in the places where people are actually talking about this comet, and ignoring it entirely leaves a gap that someone else will fill less carefully than we can fill it here. So, let's go there, carefully, with the lights on. The galactic current sheet hypothesis, sometimes called the electric universe framework, sometimes dressed up in slightly different language depending on which corner of the internet you find it in, argues that the Sun's activity is not modulated primarily by its own internal magnetic dynamo, the way mainstream solar physics describes it, but by the density and electromagnetic properties of the interstellar environment that the solar system is moving through at any given point in its journey around the galactic center. In this framing, the Sun is less like an independent engine and more like a component in a much larger electrical circuit, one that spans the galaxy itself, with the Sun's output rising and falling in response to changing conditions in the medium surrounding it. The galactic current sheet, specifically, is a real structure. That part is not invented. It is a thin layer running roughly along the galactic plane, where the direction of the galactic magnetic field reverses, a boundary between regions of opposing magnetic polarity that extends across an enormous portion of the Milky Way. The solar system does move through varying densities of interstellar plasma as it orbits the galactic center, and the heliosphere, the Sun's magnetic bubble that surrounds the entire solar system, does respond to external conditions in measurable ways. Voyager 1's crossing of the heliopause in 2012 gave us direct data confirming that the boundary between the solar environment and interstellar space is a real, dynamic, and fluctuating structure. Where the hypothesis departs from mainstream physics is in the causal chain it proposes. The electric universe framework argues that changes in the density or electromagnetic character of the interstellar medium translate directly into changes in solar output. That when the solar system moves into a region of higher plasma density, the Sun responds by becoming more active, producing more flares, more CMEs, stronger solar wind. In this framing, Solar Cycle 25's unexpected overperformance is not a surprise generated by internal magnetic conditions that forecasters underestimated. It is a predictable, even inevitable response to the solar system's position in a changing galactic environment. Proponents of this view point to a range of phenomena they argue are consistent signatures of this shift. Anomalies in cosmic ray flux reaching the inner solar system, changes in the atmospheric conditions of other planets in the solar system, long-term trends in solar luminosity, and the overperformance of Cycle 25 itself. It is a compelling narrative. It has the particular quality that all compelling alternative frameworks share. It takes real data, real structures and real anomalies, and connects them with a causal story that feels more unified and more dramatic than the mainstream explanation. And if you have spent any time in the corners of the internet where this comet is being discussed most actively, you have encountered this framework. It is not fringe in the sense of being held by a tiny number of people. It has a substantial audience, and some of that audience is genuinely scientifically literate. But this is not mainstream astrophysics, and the distinction matters, so let's be precise about where and why. The standard model of solar cycle dynamics is rooted in magnetohydrodynamics, the physics of how magnetic fields and conducting fluids interact inside the solar interior. The solar cycle emerges from the behavior of the Sun's own plasma, driven by differential rotation, the fact that the Sun's equator rotates faster than its poles. This differential rotation winds up the solar magnetic field over time, building complexity, storing energy, and eventually releasing it in the eruptions we see as flares and CMEs. The approximately 11-year cycle is a natural consequence of this internal process. The field winds up, reaches a point of maximum complexity at solar maximum, then simplifies again towards solar minimum, at which point the whole process begins again with the field polarity reversed. This is why the full magnetic cycle is actually 22 years, not 11. In this framework, the reason Cycle 25 overperformed relative to forecasts is not mysterious in principle, even if it was incorrect in practice. The initial magnetic conditions at the start of the cycle, the strength and configuration of the polar magnetic fields at solar minimum, were stronger than the models assumed. When you start with stronger initial conditions, you get a more energetic cycle. The forecasters got the input wrong. The physics was not wrong. The consensus position is that this is an error in observational data interpretation and model initialization, not evidence that an external galactic mechanism is operating. That explanation is, admittedly, less cinematically satisfying than the idea that the entire solar system is moving through a charged region of the galaxy, and the Sun is responding like an engine getting higher octane fuel. But it has considerably more empirical support, a more complete mathematical framework behind it, and does not require invoking mechanisms that have not been directly observed or measured. Here is what is genuinely worth understanding, though. Why does the alternative framework gain traction specifically during periods of high solar activity? This is an interesting sociological and epistemological question, independent of whether the hypothesis is correct. When official scientific bodies publish forecasts and those forecasts are wrong, not slightly wrong but substantially wrong in ways that are visible to ordinary people, a credibility gap opens. The people who were told in 2019 that Cycle 25 would be modest, who were then told a G5 geomagnetic storm was occurring over their heads in May 2024 and auroras were visible over Florida, are not behaving irrationally when they ask whether the models are missing something fundamental. That skepticism is a reasonable response to a real forecasting failure. The question of whether the models were missing something small and internal or something large and external is a legitimate scientific question. The current evidence points towards something small and internal. But the question being asked is not crazy, and the people asking it are not all credulous. What the electric universe framework does, in sociological terms, is provide a more emotionally satisfying answer to that legitimate question. It says, the models were not just wrong about a parameter, they were wrong about the entire framework. The Sun is not an isolated engine. It is connected to something much larger. And if that is true, then the overperformance, the comet, the timing, the infrastructure vulnerability, all of it is part of a single, coherent story with a galactic-scale cause. That kind of narrative coherence is powerfully attractive. It resolves the uncertainty in a way that feels complete. The problem is that feeling complete and being correct are different things. And the versions of this hypothesis circulating in connection with C/2026A1 frequently blur the line between the genuinely uncertain, the cometary-plasma interaction question, the solar maximum overperformance, and the speculative in ways that are not always transparent about which category they are operating in. That blurring is where the responsibility of a channel like this one becomes relevant. We can go to the edges. We should go to the edges. The edges are where the interesting questions live. But we should know where the edge ends and the open air begins. So here is where we land on this. The galactic current sheet is real. The electric universe framework is not mainstream physics and does not have the empirical support required to displace the magneto-hydrodynamic model of solar dynamics. The Cycle 25 forecasting failure was real, and the credibility gap it opened is real, and the questions people are asking in response to that gap are legitimate, even when the answers being offered are not. And the alternative frameworks gain traction during high solar activity, precisely because high solar activity creates the conditions, surprising events, official forecasts proven wrong, visible phenomena that exceed expectations, that make people receptive to explanations that feel more complete than the official ones. And all of that is context. Interesting context, worth understanding, worth being honest about. But context. The scientifically grounded tension at the center of this story remains exactly what it was before this digression, and exactly what it will be after it. A large chemically active Kreutz Sungrazer, detected unusually far from the Sun, is arriving at Perihelion on April 4th during a solar maximum that already exceeded every official forecast, entering a corona that has demonstrated elevated instability throughout this cycle, above a civilization that has quietly constructed its critical infrastructure without adequate hardening against what the Sun has always been capable of producing. Whether that civilization is responding to signals from the galactic current sheet or running on its own internal magnetic schedule, the Sun is doing what it is doing. The comet is arriving when it is arriving, and the infrastructure gap is real regardless of what is causing the solar cycle that exposes it. That is the thread. The galactic framework is a detour. An interesting one, but a detour. The thread leads to April 4th. And April 4th leads to a question that has nothing speculative about it at all. Let's walk through what April 4th actually looks like across the range of realistic outcomes, because the range is genuinely wide, and both ends of it are worth understanding clearly. This is not a moment for catastrophizing, and it is not a moment for dismissing. It is a moment for laying out what the physics actually allows, and then being honest about which parts of that we can know in advance and which parts we cannot. Scenario 1. C/2026. A1 survives perihelion largely intact. This is not guaranteed, but for a nucleus estimated at 2 kilometers, it is genuinely possible. Lovejoy survived. The 1882 comet survived. A sufficiently large cohesive nucleus may have the thermal inertia to punch through the corona without disintegrating. Think of it less like an ice cube dropped into a furnace and more like a boulder dropped into a river. The river is violent. The boulder is still a boulder on the other side. If this happens, what follows perihelion may be one of the most spectacular naked-eye astronomical events since the modern era of continuous observation. Forward-scattering geometry is the variable that makes the optimistic brightness predictions feel almost unreasonable until you understand the physics. When a comet passes between Earth and the Sun, sunlight scatters off the dust particles in its coma and tail in a way that dramatically amplifies apparent brightness, orders of magnitude beyond what standard reflectivity models would predict from any other viewing angle. It is the same reason a dusty windshield that looks fine when you are driving north becomes nearly opaque when you turn and drive directly into the setting sun. -7 or beyond in this scenario is not alarmist. It is within the range that the physics of forward scattering can produce for an object of this size at this geometry. People standing in the daytime sky on April 4th or the days immediately following could look carefully toward the sun. With appropriate eye protection, please, I am not responsible for your retinas, and see a bright streak that their great-grandparents would have called a portent from God. It would be the kind of event that gets remembered, the kind that gets painted, the kind that, if it happens, will make every person who watched this video feel very smug about having paid attention in March. Scenario 2. The comet fragments and fades. The tidal forces at that perihelion distance are immense. The differential gravitational pull across the width of a 2-kilometer object, at that proximity to the Sun's mass, is capable of literally pulling the nucleus apart along any structural weakness. The thermal stress from the corona adds another layer of violence to that process. The comet may simply break apart into pieces too small to survive independently, each fragment quickly evaporating in the radiation field before it can clear the corona. From Earth's perspective, SOHO's coronagraph cameras would show a brief brightening as the fragments entered the field of view, a smear of light that flares and then dims, and then nothing. A disappointing end to a dramatic opening act. The comet of the century becomes a footnote, another entry in the long list of comets that promise more than they delivered, and there is a long list. In this scenario, the solar physics question becomes largely academic. Smaller plasma filaments from fragmented debris are less likely to produce the kind of sustained coronal perturbation that concerns the minority of researchers paying close attention to that mechanism. The comet dies quietly, and the Sun moves on without noticing. Scenario 3 is the speculative one, and it deserves to be described carefully because this is where the language needs to stay precise. The comet, or its fragments, enters the corona, and the plasma interaction with an already stressed magnetic flux rope produces a perturbation sufficient to push an unstable configuration past the threshold for reconnection, contributing to the initiation of a significant coronal mass ejection. Each word in that sentence is doing work, contributing to, not causing, not triggering in a simple mechanical sense. The corona is already a system under stress during solar maximum. The comet, in this scenario, is not a cause. It is the last variable in a chain of conditions that were already most of the way to an outcome. The far-side geometry of the perihelion is a genuine moderating factor here, and it is worth being clear about what it means. The April 4th perihelion occurs on the hemisphere of the Sun facing away from Earth. A CME launched from that location would propagate outward in a direction initially away from us. It would not be aimed at Earth like a bullet. However, and this matters, CMEs are not perfectly directional beams. They expand as they travel. And as the Sun rotates in the days following perihelion, any active region associated with the event rotates toward the Earth-facing side. The immediate risk window is substantially lower than if perihelion were happening on the near side. But the window does not close to zero. Satellites positioned at the L1 Lagrange point, roughly 1.5 million kilometers directly between Earth and the Sun, would measure the change in solar wind conditions as any event propagated outward. There would be warning, probably hours, possibly less. The question of whether hours of warning would translate into effective protective action across the modern infrastructure systems we discussed earlier is a separate question, and it is an uncomfortable one. And the answer as of right now is probably not enough. The probability chain for scenario 3 producing a direct significant impact on Earth remains low. Say that clearly. Each link, perturbation, reconnection, CME launch, Earth-directed trajectory, sufficient magnitude is individually uncertain, and all of them must connect simultaneously. The combined probability is low, but here is the thing about low probability events that we consistently get wrong as a species. We treat low probability as equivalent to not worth thinking about. Those are not the same thing. A 1 in 100 chance of losing everything you own is low probability. It is also the kind of thing a rational person buys insurance against. We have not bought the insurance. That is a choice. It may be the right choice, but it is a choice that was made largely without public discussion, and April 4th is a reasonable moment to notice that. What is emphatically not low probability is the continuation of solar cycle 25, regardless of what happens on April 4th. The cycle does not end on April 5th. The sun does not look at the calendar, note that the comet came and went without incident, and decide to calm down. Active regions will continue developing across the solar disk for months. The flare rate will remain elevated. The G5 class event potential that May 2024 demonstrated, auroras over Florida, over Texas, over latitudes that had not seen them in a generation, does not disappear because a comet came and went. The elevated state of the solar maximum is the background condition. The comet is a single event within it. When the comet is gone, the background condition remains. The infrastructure vulnerability is the same. It existed before anyone in Chile pointed a telescope at a faint smudge of light in January and realized what they were looking at. It will exist on April 5th and in June and next year. The high voltage transformer replacement gap remains. The GPS timing dependency woven through financial systems and power grids remains. The satellite constellation that has expanded faster than the hardening standards designed to protect it remains. These are not problems the comet created. They are problems the comet is briefly illuminating, the way a lightning flash illuminates a landscape you are already standing in. What C/2026 A1 does in this framework is function as something like a stress test made visible. It arrives, it is beautiful or it isn't. It perturbs the corona or it doesn't. It gives us a dataset or it gives us a quiet disappearance. And then it is gone, and the sun keeps burning, and the infrastructure gap keeps existing, and the cycle keeps cycling. There is something genuinely worth sitting with in the observation that we have built monitoring systems sophisticated enough to detect a 2-kilometer comet at 1 astronomical unit from the sun in January, calculate its orbital trajectory down to fractions of an astronomical unit, model its likely brightness across a range of survival scenarios, and then observe in near real time as it plunges into the solar corona in April. SOHO will be watching. The Solar Dynamics Observatory will be watching. Helioseismologists and space weather forecasters around the world will have their instruments pointed at the precise region of the corona where this object arrives. We will understand what happens on April 4th better than any previous generation could have imagined understanding an event like it. The knowledge is extraordinary. And yet the gap between knowing and being prepared remains exactly as wide as it was before we knew the comet was coming. April 4th, 2026 answers one question. It tells us whether this particular comet survives this particular approach during this particular solar maximum. It may give us a sky show that people describe to their grandchildren. It may give heliophysicists a dataset that reopens a debate about cometary plasma interactions that has been sitting half-closed since 2011. It may give us nothing dramatic at all, just a quiet dissolution into the sun's light, a few remarkable coronagraph images, and an astronomy community that shrugs and moves on to the next object. But the larger question, the one that does not get answered on April 4th, the one that does not have a perihelion date attached to it, persists. We live on a planet orbiting a star that has, throughout all of recorded history, been periodically willing to remind us of its actual scale. We have responded to that knowledge by building the systems our civilization depends on with what can only be described as cheerful faith that the sun will continue to cooperate. Solar Cycle 25 has already told us, clearly, that faith has a ceiling. April 4th is one data point. The sun keeps burning after it. And the question of whether we are genuinely ready for the event that is not just a data point, the one without a date, the one that arrives without a comet to warn us it is coming, that question does not close on April 5th. It just keeps waiting for an answer.